Module 1, Lesson 8, Bairstow's Method. For this module, we will then cover different techniques that iteratively solve nonlinear polynomial functions. The Bairstow's method is one of which. This particular technique incorporates synthetic division, so I'll run down synthetic division, the different possible outcomes when using this technique, and some sample problems on applying this technique. Nonlinear polynomial functions or algebraic equations normally take this given standard form, whereby your respective an is a constant coefficient of your given polynomial equation with variable x raised to a certain n degree of positive integer. The roots of your polynomial function depend on your n or degree. The roots will either be a real number or a complex conjugate, although there are a lot of empirical formulas that evaluates the root of your nonlinear polynomial function. Still, iterative techniques are often preferred. One of these iterative techniques is known as the Bairstow's method, which utilizes this general quadratic function whereby your parabolic equation is equivalent to x squared minus rx minus s, where r asterisk and s asterisk represents coefficient of your quadratic factor f2 of x, shown to be the exact quadratic factor of your given polynomial function. Note that in order to evaluate the new value r and the new value s, it is simply equivalent to the previous r plus delta r, or previous s plus delta s. Therefore, r and s refers to the initial values of r and s, and delta r and delta s implies changes in the values of your r and s. In order to establish then the changes in your r and s, it is actually obtained by evaluating this system of linear equation, whereby you're given C2 delta r plus C3 delta s is equal to negative B1, and the other equation C1 delta r plus C2 delta s is equal to negative B0. The linear equation contains coefficients that were derived from applying synthetic division to the given function with the use of the initial values r and s. The coefficients B0, B1 are the first level quotients, while the coefficients C1, C2, C3 are the second level quotients of your synthetic division. To give you an idea or a rundown how synthetic division is applied in evaluating the quadratic equation, let's take a look at this given cubic polynomial function, wherein we're given a coefficient a3x3 plus a2x squared plus a1x plus a0. The usual process involving your synthetic division takes the coefficients a3, a2, a1, a0 and subjects them into a division-like operation on your respective roots. However, for this given technique, we will subject them to root values r and s. Based on the initial value of your r and s normally given on your problem, which I have intentionally set to be 0 on this given illustration, in order to evaluate then the quotient B3, you simply bring down A3. In order to evaluate then the quotient B2, you multiply r times B3 and add it to A2. In order to establish then the quotient B1, you multiply r with B2, add it with s times B3, and add it to your coefficient A1. To evaluate then the remainder B0, you simply multiply r with B1 and add it to the product of s times B2 and add it to your coefficient A0. This represents then the first level quotients. In order to establish the second level quotients, you will then subject this first level quotient starting from B3 all the way to B1 only, since B0 represents your remainder. By subjecting them to synthetic division again using your initial value r and s, which are both equal to 0, you would then end up with a second level quotient to be evaluated like this. So you simply bring down B3, which will then establish your second level quotient C3. In order to evaluate C2, you multiply R with C3 and add it with your quotient B2. To evaluate C1, you multiply R with C2, add it to the product of S times C3, and add it to your quotient B1. After evaluating then these coefficients, you could now evaluate your linear equation and solve for delta R using this formula and delta S using this formula. After solving for delta R and delta S, you could now establish new values of R and new values of S. We then check whether we ended up with the correct values of R and S needed for our quadratic equation. Therefore, we then check whether this particular value satisfy our terminating condition, which is noted to be delta R over new value of R times 100%, and for your S, delta S over new value of S times 100%. Note the similarity of this particular terminating condition to your relative error, since the change in R often occurs to be the new value of R minus the previous value of R, all over the new value of R. Hence, this particular terminating condition is more or less similar to your relative error. Note that both R and S are coefficients of your quadratic factor f2 of x. Therefore, both variables should satisfy the terminating condition before you stop the process. The process is then repeated by using the computed new values R and S as previous values of R and S for your next synthetic division. If you have satisfied then the terminating condition, then the root formula is simply a derivative of your quadratic equation, which is evaluated to be R plus minus square root of R squared plus 4S all over 2, which if you look at it is similar to your quadratic equation applied to your given quadratic function x squared minus Rx minus S. What then would be the possible outcomes when I'm using this particular technique? Let's say if you're given a polynomial function that is a fifth order or even higher, then in order to evaluate for all the roots of your respective fifth order polynomial function after obtaining a quadratic function f2 of x, then you simply deflate the function, which is a fancy term for polynomial division, and then apply these factors R and S that you have previously computed for your deflated function, and then use Bairstow's method again to solve for the remaining roots. The other possible outcome is if you're given a fourth order polynomial function, upon which after solving your quadratic function f2 of x using Bairstow's method, in order to evaluate then the remaining two other roots for your given function, then you simply deflate the function or divide your fourth order function by your second order function, giving you a second order function, and then simply subject that to your root formula again. The third possible outcome is if you're given a third order polynomial function, then in order to obtain the remaining roots after deriving a quadratic function, then simply deflate your given function or divide x cubed with your quadratic factor. And then the deflated function is either equated to 0 or simply subjected to this formula in order to solve for the last root. Let's try to apply that on this given example. Let's say we're given this cubic function and we're asked to evaluate all of its roots using the initial value R and S, having a terminating condition for R and S to be equal to less than or equal to 0.7115%. We begin the process by using synthetic division on your given polynomial function. Getting then the coefficients for your polynomial function gives us an A3 value of 1 an A2 value of -4, an A1 value of 1, and an A0 value of -10. Using now the initial values R and S equal to 0, we will then apply the synthetic division based on what we have previously shown. Therefore, your quotient B1 would simply be 1, your quotient B3 would simply be 1, your quotient B2 would simply be -4, your quotient B1 is still 1, and your quotient B0 remains -10. Subjecting this to your next level synthetic division gives us a C1 value of 1, a C2 value of -4, and a C3 value of 1. We then use these coefficient values for your linear equation in order to establish then the change in R and the change in S. Thus, the change in R and S are obtained by this given linear equation, whereby you have -4 delta R plus 1 delta S is equal to -1, and 1 delta R plus -4 delta S is equal to 10. Obtaining then and solving delta R and delta S gives us a delta R equal to -0.4 and a delta S equal to -2.6. Hence, our new value of R would be the previous R, which is 0, plus -0.4 gives us -0.4. Our new value of S then would be 0, plus the change in S, which is -2.6, therefore gives us a new value of -2.6. If we then try to establish then the errors for this given particular values of R and S, we'd end up with both having 100%. Thus, we simply repeat the process since the terminating condition was not satisfied. I then set this new computed R as previous R to be -0.4 and this new computed value of S to be previous S, which is -2.6. And then I repeat the process. The process begins again on your next iteration by applying synthetic division on your given particular cubic function. Thus, extracting our coefficients to be like this. Applying now our R to be -0.4 and S to be -2.6 gives us a coefficient B3 value, which are your first level quotients to be 1, your B2 to be -4.4, your B1 to be 0.16, and your remainder B0 to be 1.376. Notice that as we continue the process, your remainder B0 should eventually approach 0, showing us that we have evaluated one of the quadratic factors given on your cubic function. Continuing then our synthetic division, in order to evaluate the second level value C's, we then continue on the synthetic division, thus giving us a C3 value of 1, a C2 value of -4.8, and a C1 value of -0.52, which eventually leads us to this linear equation, having an equation 1 to be -4.8 delta R plus 1 delta S is equal to -0.16, and a second equation equal to -0.52 delta R plus -4.8 delta S is equal to -1.376. Solving then delta R and delta S would give us a delta R of 0.091 and a delta S of 0.2768. Solving then for your new value of R gives us the previous value, which is -0.4, plus the change in value, which is 0.091 in R, which gives us a new value of R to be -0.309, and a new value of S to be the previous S, having a value of -2.6, plus the change in S, which is 0.2768, gives us -2.3232. Solving then for the error, your error at R is computed to be 29.4506%, while the error at your S is computed to be 11.915%, which eventually leads us to repeating the process. Thus, we then set your new computed R value as previous value of R, which in this case now is equivalent to -0.309, and your new value of S reverted as the previous value of S, having a value of -2.3232. We then repeat the process again by subjecting your cubic function into synthetic division to solve for the coefficients needed to evaluate your delta R and delta S. Applying synthetic division on your given cubic polynomial function using the R value of negative 0.309 and an S value of negative 2.3232 leads us with a B3 value equal to 1, a B2 value equal to negative 4.309, a B1 value of negative 0.0083, and a B0 or remainder value equal to 0.0081. Notice that the B0 now is almost approaching your zero value. Hence, it implies that we are getting closer and closer to the true values of R and S. Subjecting these first level quotients again to synthetic division leads us to your second level quotient to be a C3 of 1, a C2 value of negative 4.618, and a C1 value of negative 0.8879. This coefficients then leads us to a system of linear equation equal to negative 4.618 delta R plus 1 delta S is equal to negative 0.0083. And the second equation equal to negative 0.8879 delta R plus negative 4.618 delta S is equivalent to negative 0.0081. Solving delta R and delta S to be 0.0021 and a delta S equal to 0.0014, which eventually gives us a new value of R to be the previous negative 0.309 plus the change 0.0021 leads us to a new value of R to be negative 0.3069, and a new value of S computed to be the previous S, negative 2.3232, plus the change in S, 0.0014, gives us a new value equal to negative 2.3218. When checking the error, your R gives us an error of 0.6843%, which eventually satisfies our terminating condition, and your S gives us an error of 0.0603%, which eventually satisfies again your terminating condition. Thus, this happens to be the correct values of R and S. Subjecting them to your quadratic function gives us a quadratic factor equal to x squared plus 0.3069x plus 2.3218, which eventually leads us to a root computation equal to this solution with a root value of negative 0.1535 plus minus j 1.516, showing us that this particular quadratic function gives us a complex conjugate root for our given cubic polynomial function. We then deflate your cubic function by dividing your cubic function x cubed minus 4x squared plus x minus 10 with your quadratic factor, which is x squared plus 0.3069x plus 2.3218, which eventually gives us a quotient equal to x minus 4.3069, which is a linear function. In order to establish then the last root, we simply equate our given function to 0, which eventually gives us the third root to be equivalent to 4.3069, which we have established and solved using the different techniques involved in your polynomial function. This is another example stated on the book, whereby we're asked to employ Bairstow's method in order to determine the roots of your given polynomial function, which is a fifth order polynomial function given to be x raised to 5 minus 3.5x raised to 4 plus 2.75x cubed plus 2.125x squared minus 3.875x plus 1.25, with an initial guess of R and S equal to negative 1, and a terminating condition of ER and ES to be less than or equal to 1%. This particular example shows us possible outcome 1, while the previous example shows us possible outcome 3. Let's try to evaluate then the root. The solution involves in synthetic division on your fifth order polynomial function, which eventually leads us to a first level quotient equal to B5 equal to 1, a B4 of negative 4.5, a B3 of 6.25, a B2 of 0.375, a b1 of negative 10.5, and a b0 equal to 11.375. Subjecting this first level quotients to synthetic division again gives us a C5 of 1, a C4 of negative 5.5, a C3 of 10.75, a C2 of negative 4.875, a C1 of negative 16.375, which eventually leads us to a linear equation now equal to negative 4.875 delta R plus 10.75 delta S is equal to 10.5. And a second equation equal to negative 16.375 delta R plus negative 4.875 delta S is equal to negative 11.375. Evaluating then your delta R and delta S gives us an answer of 0.3558 and a delta S equal to 1.131381. Hence, your new value R is computed to be the previous value negative 1 plus 0.3558, which leads us with a new value of negative 0.6442, and a new value of S equal to negative 1 plus 1.1381, which eventually leads us to a new value of 0.1381. An error for R gives us 55.23%, and an error for S gives us an error of 824.1%, which eventually shows us that we need to repeat the process. Hence, we set your previous value as negative 0.6442 and your previous value of S to be 0.1381, and we repeat the synthetic division on your given fifth order function. Repeating then, the synthetic division gives us a quotient B5 equal to 1, a B4 of negative 4.1442, a B3 of 5.5578, a B2 of negative 2.0276, a B1 of negative 1.8013, and a B0 of 2.1304. While subjecting that to your second level quotient gives us a C5 of 1, a C4 of negative 4.7884, a C3 of 8.7806, a C2 of negative 8.3454, and a C1 of 4.7874, which leads us to a linear equation equal to negative 8.3454 delta R plus 8.7806 delta S is equal to 1.8013. And a second equation equal to 4.7874 delta R plus negative 8.3454 delta S is equal to negative 2.1304. The changes in your R and S are then used to evaluate then delta R, having a value now of 0.1331 and a delta S equal to 0.3316. Solving then for the new value of R leads us to this solution, which gives us a new value of negative 0.5111 for R, and a new value of S with this solution having a value of 0.4697. With an error associated with your R to be 26%, and an error associated to your S giving you 70.6%. Thus, we simply repeat the process, setting your previous R to be negative 0.5111, and your previous S is now set as 0.4697. The computation can be continued with the result after 4 more iterations, converges on the values of R to be equivalent to negative 0.5, having an error of 0.063%, satisfying our terminating condition, and an S value of 0.5, a new value of S 0.5, having an error of 0.04%, which then satisfies our terminating condition, which leads us to a given quadratic equation equal to x squared plus 0.5x minus 0.5. Establishing then the root of your quadratic function gives us this solution, ending up with the root equal to 0.5 and negative 1, which evaluates 2 real numbers. We then repeat the process by deflating your given function, which is a fifth order polynomial function, and dividing it by your quadratic factor, giving us a deflated cubic quotient to be equivalent to x cubed minus 4x squared plus 5.25x minus 2.5. We then subject that cubic function back to Bairstow's method in order to establish the remaining 3 roots, which should eventually gives us a new value of R and S using the previous calculated value as initial value for your Bairstow's method of having R equal to negative 0.5 and then S equal to 0.5 on your cubic function. After 5 iterations, it then yields an R value equal to a new value of R equal to 2 and a new value of S equal to negative 1.249, which is then used for your quadratic function, which is x squared minus 2x plus 1.249, which solves the root to be 1 plus minus j equal to 0.499 or 1 plus minus j.5, which implies that this particular quadratic factor gives us a pair of complex conjugates. We then deflate our cubic function by dividing your cubic function with your quadratic factor, having a solution like this, giving us a deflated first order polynomial function to be x minus 2. In order to establish then the last remaining root, we simply equate that linear function to 0, thus giving us the last root to be x equal to 2. That is how Bairstow's method evaluates your fifth order polynomial function or higher. This ends the module.